This animated diagram shows a classic physics setup: 2-point charges, A and B, interacting with a single predictable line of force. We calculate that using Coulomb's law. But what happens to that specific calculation if we introduce a third charge into the system? The original force between A and B remains exactly the same. The presence of charge C doesn't block or weaken it. Instead, charge C simply creates a second, completely independent force on charge A. This is the principle of superposition. To find the total effect on charge A, we don't need to reinvent the equation. We just calculate the individual force from every other charge in the system, one at a time, and find their vector sum. This means even the most complex cluster of particles is ultimately just a collection of simple, independent pairs acting at the same time. In this animated diagram, 3 charges are arranged at the corners of an equilateral triangle. Our goal is to find the total net force acting on the charge at the top apex. Because force is a vector, we cannot simply add the magnitudes together. To begin, we must isolate the top charge and determine the specific direction of every force acting upon it. Look at the interaction between the top charge and the bottom left charge. Since both are positive, they repel. The bottom left charge pushes the top charge away, creating a vector arrow angled up and to the right. Now look at the bottom right charge. It is negative, so it attracts the top positive charge. This pulls the top charge inward, along the edge of the triangle, toward the bottom right. Mapping these physical polarities onto directional arrows gives us the precise angles we need to solve the rest of the problem using trigonometry. In an equilateral triangle, all sides are equal. Since the charge magnitudes are also identical, Coulomb's law dictates that the magnitude of both force vectors is exactly the same, even though they point in different directions. Combining these two vectors using the parallelogram law reveals the final path of the top charge, a single net force vector pointing straight to the right. Now it's your turn. Pause the video and determine the net force acting on the bottom left charge instead. Be sure to draw the arrows first. Let's reveal the solution. First, the top positive charge repels the bottom left charge, pushing it downward and to the left. Second, the negative charge at the bottom right attracts the bottom left charge, pulling it horizontally right. Applying the parallelogram method to these two forces results in a net force vector that points down and to the right. Accurate vector addition depends entirely on correctly identifying those initial directions based on the signs of the charges. Consider a scenario with 3 identical positive charges at the corners of a triangle, all pushing on a target charge placed in the exact center. Calculating components for 3 angled vectors would be a massive time drain. However, we can use the geometry of the system to skip the math entirely. When identical forces push from equally spaced angles, the symmetry causes them to perfectly cancel each other out. The net force is 0. Always check for symmetry before starting calculations. For any multiple charge problem, follow this workflow. 1. Isolate the target. 2. Draw the direction arrows. 3. Calculate the magnitudes. 4. Add the vectors. Success with the principle of superposition comes from isolating the individual interactions first. Once the pairwise forces are clearly defined, the final result is just a matter of combining the vectors.